Hi everyone, this is Aaron with Design and Digital Systems Lab for Section 1 for Dr. Ahalabi. Today I'm presenting Lab number 3, the Arithmetic Logic Unit. This Arithmetic Logic Unit takes two 6-bit inputs and a 4-bit select input. The lower 2 bits of the 4-bit select input will control each of the independent operations of the adder, multiplier, logic unit, and shifter. And the upper two bits of the 4-bit select will control the output of the multiplexer, which is selecting one of the 4 streams from the independent units. So let's take a look at the table to verify what these select inputs are doing. For the adder takes the lower 2 bits from 0 to 3. For input 0, we have A plus B and just the sum, not the carry. For input 1, we have A plus B, but only the carry. For input 2, we have A minus B using 2's complement method without the borrow. And for input 3, we have A minus B using 2's complement method, but just the borrow. For inputs 4 through 7, the lower select bit, least significant bit of the 4-bit inputs, 0 and 1, will control either the low 6 bits of the product of A times B or the high 6 bits of the product of A times B, because as you may recall, we need to have A plus B bits to represent the full product of A and B, but this ALU only has a 6-bit output, so we need to select between either the low or the high 6 bits. For the logic unit, we have inputs 8 through 11. Input 8 will represent the bitwise NOT of A. Input 9 will represent the bitwise AND of A and B. Input 10 will represent the bitwise OR of A and B. And input 11 will represent the bitwise XOR of A and B. For the shifter, we have inputs 12 through 15. However, 12 and 13 will both produce the same result. That's why we have an X here in the table for the least significant bit. So inputs 12 and 13 will both perform a logic shift of A by B bits to the left, where B is the lower 3 bits of B. For input number 14, we have a logic right shift. And the difference between a logic and an arithmetic shift is that a logic shift will pull in zeros, and an arithmetic shift will pull in the most significant bit to retain the sign of the number, the sign magnitude of the number. And so wrapping that up, for input 15, we have an arithmetic right shift of A by B bits. So now that we understand how all of the selects are going to control the operation of the ALU, let's take a look at how we're going to map the pins for the in and out. So we have switches 0 through 5 mapped to the input B for the 6 bits of input B. We have switches 6 through 11 mapped for the 6 bits of input A. We have switches 12 through 15 mapped for the inputs, the select inputs. And for the output, we have LEDs 0 through 5 for the 6 bits of the output. So now that we have the ins and outs mapped for the board, let's go ahead and run through some of the test cases to demonstrate that the board is correctly working. We'll start with the first test case where we have A set to 4 and B set to 2. So I'll start the video on the right. This is pre-recorded so that I could do this voiceover. And here I'm setting B to 2 and A to 4. You can see for input 0 that we have the addition, which is 6. 4 plus 2 is 6. For input 1, we have just the carry, which is 0. For input 2, we have the difference of the 2, which is 2. 4 minus 2 is 2. For input 3, we have just the borrow, which using 2's complement results in a carry of 1. For input 4, we have the low 6 bits of the product of A and B, which is 8. And for input 5, we have, that was input 4. For input 5, we have the high 6 bits, For input 6, we again have the low 6 bits. For input 7, we have the high 6 bits again. And for input 8, we're going to have the bitwise not of A. For input for input 9, we'll have the bitwise AND of A and B. For input 10, we'll have the bitwise OR of A and B. And for input 11, we'll have the bitwise XOR of A and B. For input 12, we're going to shift A to the left by 2 bits, and the same for 13. For input 14, we're going to shift to the right by 2 bits, because B is a binary 2, we're shifting to the right by 2 bits. And for input 15, we're doing a arithmetic right shift by 2 bits. In this case, the leading significant bit was 0, so we brought in zeros. So now that we've tested the first case, we're going to take a look at the second case, and we're going to do the exact same thing that we just did for A equals 49 and B equals 50. So here I'm setting the inputs for A to be 49 and for B to be 50. We can see that for input 0, we have the sum of A plus B without the carry. This results in a decimal value of 35 in the binary representation you see there on the screen. For input 1, we have just the carry of A and B, which is a 1. For input 2, we have the difference of A and B, which results in 63, because we can't hold the carry bit. For input 3, we have the borrow of A and B, which is 0. For input 4, we have the product of A times B, but the low 6 bits, and now the high 6 bits for input 5. Input 6 again is the low 6 bits. Input 7 is again the high 6 bits. Now we're shifting to input 8. Input 8 is the bitwise not of A. Input 9 is the bitwise AND of A and B. Input 10 is the bitwise OR of A and B. Input 11 is the bitwise XOR of A and B. Input 12 is the logic shift of A by how many bits? 3 bits. 3 bits to the left. And again for the next input. And then we have a right shift by 3 bits for 14. For input 15, we have an arithmetic right shift by 3 bits. Now here I'm setting up for the final test case where A and B are both 63, meaning all of the inputs are on for A and B. And we're going to cycle through all of the select combinations again here. So we can see for 0, it was the sum of A and B, which resulted in 62. For input 1, we have A plus B, but just the carry, which was 1. For input 2, we have the difference of A and B, since they're the same, it's 0. For input 3, we have a carry of 1, which is just the borrow of A and B. Again, we're using 2's complements method, so we end up with a carry of 1 after the addition. For input number 4, we have the product of A and B, the lower 6 bits, which is a 1. For input 5, we have the upper 6 bits of the product. Input 6 is again the lower 6 bits. And then input 7 will be the upper 6 bits. For input 8, we're going to have the bitwise not of A, which is all zeros, because every input in A is set high. For input 9, we're going to have the bitwise AND of A and B, so they're all high. The bitwise OR of A and B, again, also all high. And for input 11, we'll have the XOR of A and B, which is all zeros, since the bits are all the same. For 12, we're going to have a left shift by 15 bits. And again, if left shift by 15 bits logically, so we're bringing in zeros. For 14, we'll have a right shift by 15 bits. I'm sorry, I'm saying 15 bits, I mean 7 bits. We're using the lower 3 bits of B, which would be binary 7. And then as you saw for 15, for input 15, we have an arithmetic shift to the right by 7 bits, and so we brought in all ones. Okay, so that's going to mark the end of lab number 3. Hopefully this presentation was decent enough to show all of the configurations for the ALU. Thanks for watching. Take care.